problem, which is question 4, which is this Bragg's law bubble raft. So 1947, Bragg used this bubble raft to model how dislocations move, and you can actually measure stress strain curves. And this is kind of a fun lab that I used to run when I was a TA in my graduate school days. But anyways, apparatus can be seen below. Bubble raft with W placed between two plates, initial length apart. The adjustable stage and compression flap moves, so it compresses this bubble raft, compresses here, which in turn exerts a force on the force transducer, piezoelectric. Force converted to voltage, which can be read on the voltmeter. We must correlate the force to voltage. We do so by calibrating using a pendulum. So the force of the pendulum is just this, as all my mechanical engineering students and bioengineering students know. That expression, I don't know, I'm a material science person, but anyways, you can do the pendulum. So m is the mass of the nut, g is gravitational constant, x distance, arm, etc., etc., etc. We then correlate the force to voltage using a force correlation factor, FCF, and then where F is the force, the pendulum, V is the output voltage read from the voltmeter. The mass of the nut and the voltage was measured 10 times. Okay, here we go. So our mass, or our x bar of our mass, was equal to 320 milligrams with a sample standard deviation of 1 milligram. So our S of M is equal to 1 milligram right here. So mean mass here, standard deviation here, and the number of our mass was measured 10 times equals 10. So and a sample mean, so the mass and the voltage is measured 10 times. So the number of voltage is also 10. We found that the x bar of our volts was equal to what? 4 volts. And then finally, sample standard deviation of 1 millivolts. So this is where we want to be careful. So standard deviation of volts is equal to 1 times 10 to the minus 3. And actually, we'll do the same thing here. Keep everything in, actually, we'll keep everything in milligrams right here. So 1 milligram. But we want to keep this in volts. So 1 times 10 to the minus 3 volts. Nominal value of x. So nominal value of x to be 5 centimeters. So our x equals 5 cm, just the nominal value. The height, h, is equal to 20 centimeters. And we used a really bad ruler where the best we could resolve was plus or minus a centimeter. So our uncertainty in our u in the height is equal to 1 times 10 to the minus 3. Again, we want to make sure that these are all meters. So 5 times 10 to the minus 3, 20 times 10 to the minus 3. So uncertainty in height, uncertainty in our x is equal to 1 times 10 to the minus 3 meters. The voltmeter used was much better, having a resolution of 1 microvolt. The uncertainty in the voltage was 1 times 10 to the minus 6 volts here. So we are asked, what is the uncertainty calculated in the FCS, expressed as a percentage? What contributes to more total uncertainty, precision, or bias error? So our FCF equation was given above here. So our FCF is equal to mgx over h times v, right? So force divided by voltage, so right here. So our FCF is a function of 4 variables. Actually, is a function of m, g, x, h, and v. G is equal to 9.8, so that is our gravitational constant. Let's make sure the units of gravitational constant. Say acceleration, so let's go ahead, the 9.8. So actually, that's not our gravity of Earth, g. Actually. So 9.8 meters per second squared. So g is equal to 9 meters per second squared, not our gravitational constant. Excuse me. But again, I'm not a mechanical engineer. I'm just a plain old simple country material scientist. But anyways, so these are kind of our variables here. So we always kind of want to break down, where do we have precision uncertainty, where do we have bias uncertainty. So anything about the gravitational constant. So there's no uncertainty in g, and that is not measured at all either. So precision error in g is equal to 0. So we can cross that one off the list. What about mass? So let's go ahead. Mass. Now we're told the mass and the voltage, but we're not really told how we're measuring the mass. So there is no uncertainty in the mass. So that is equal to 0. What about the uncertainty in H? Yes. So we're going to take that partial. What about V? Yes. And X as well. So we're going to have bias error in, so we'll have bias error not in this, but in here, here, and here. So we have bias error in these three. What about precision error? We have precision error in M. You better believe it. So precision error in M. So we are going to have, we're also going to have some bias error in M. What about voltage? Yep, I'm going to have precision error in voltage as well. And let's see, anything else? So do I measure any other values multiple times? No, I'm just given the nominal values of X. So I don't have any precision error. Precision error in X is equal to 0. Precision error in H is equal to 0. And I do have some precision error in voltage in them. So let's go ahead and let's kind of put all this stuff together in a notebook. So I'm going to go ahead, create a new notebook. Oops, I don't want a style notebook, unfortunately. So let's go ahead, let's do a new notebook. Let's clear everything. So file, evaluation, quick kernel, local. Here we go. So let's go ahead and start to kind of calibrate these values. So I have, let's start to kind of type these in. So I have my xm equals 320 times 10 to the minus 3. I actually want to do it in, actually 320, because I have, basically, I want to work with kilograms. So I could do it to 10 to the minus 6 as well. So 10 to the minus 6. But again, you could kind of work out these values yourself. This is a force correlation factor. So standard deviation of m is equal to 1 times 10 minus 6. Again, if I want to go from milligrams to kilograms, nm equals 10. I have xv equals 4. I have sv equals 1 times 10 to the minus 3. I have nv equal to 10. What are some other values? I'm going to wait and plug in my values of x and h and all those values as well, but I'm going to do I have some uncertainty. Uncertainty in h is equal to 1 times 10 to the minus 3 meters. Uncertainty in x equals uncertainty in h, and uncertainty in v equals 1 times 10 to the minus 6. So those are some of the values that I have and I can now work with. So I'm going to go ahead and calculate, I'm going to also derive my FCF is equal to basically m times g times h. Actually, let's go ahead up here. So m times g times x divided by h times v. So let's go ahead and take the partial derivatives that I need. So I know I'm going to have some uncertainty in h, x, and v. So I'm going to do basically dh, which is going to be d FCF times h, or uncertainty in h. I'm going to do the same thing here. So I'm just going to do this with respect to x. Then I'm going to do this with respect also to right here. This is going to be uncertainty in the volts. So V, so volts. So there we go. So I could do my bias now. My bias equals square root of, I'm going to do d dh times uncertainty in h divided by FCF. And I'm going to do that. Do that squared plus my dh, actually dx times ux divided by FCF squared plus my dv times uv divided by FCF squared. So again, this is going to be giving everything in terms of my fraction. So I'm going to plug in and I can do slash dot h goes to, where's my h value, my nominal values. Let's go back over here. So h is 20 centimeters. So I'm going to do slash dot h goes to 20 times 10 to the minus 2. 20 times 10 to the minus 2. My x goes to 5 times 10 to the minus 2. And my v goes to xv. So those are those values. Plug it in. Let's look at this numerically. Oops, not nv. So this is going to be about 2%. So again, because this is a dimensionless fraction. Now I need to look at where do I have some precision error? Well, I know I have precision error in my mass. So PM is equal to, let's see, I need my T alpha over 2. So remember that precision error, M, X, G, we already know those values. So actually let's define G as well. But we may not even need it. So we may not even, so there was no precision error, excuse me. So we had nothing in G, we had nothing in X, we had nothing in H, we had mass, precision mass in volts. So let's go ahead and remember precision error in any, in mass is going to be T alpha over 2 nu times S mass over square root of n. So we know n is equal to 10. So now we need to go back and look up we know we're working on 95% confidence interval. So I'm going to look at a T of 0.025 and then 9. So let's go ahead and look at that value. I'm going to pull up not my DSC lab, even though I love my DSC lab, and I'm sure everyone else does as well. But let's go ahead and look this up. Look at this value here. So, oops, actually, not this in this lecture. Let's go to lecture 3. My very, very useful T function. So let's go T of 025 to a value of 9. So 2.262. So discard 2.26. So my precision error, my P of M is going to be 2.262 times SM divided by square root of NM. And then I'm going to take this whole thing, actually let me make sure. Again, I'm just a little bit paranoid here. So I'm going to do this, and I'm going to divide by XM to, again, make this a dimensionless fraction. So that's my PM. I'm going to do the same thing for my PV. Let me see, my PV equal to SV, NV, XV, that value here. So now we can see kind of where our error is dominating. And as you might expect, we are definitely dominated by our bias error. It's an order of magnitude greater than this, and 2 orders of magnitude basically greater than this. So our bias error is completely dominating. Great. So to calculate stress, we would use an equation here. So how'd you go about calculating the uncertainty in sigma? But don't calculate and describe with equations in text. So really the only thing that changes here is our volts. So our function would be, it's mgx over hv. If we multiply it, that's equal to our FCF. Multiply it by voltage. So we don't have anything to concern now about voltage. And then we just add this additional width. And the width, I mean, we're not given what the value is multiple times, but assuming that we measured it with the same, we'd have some same uncertainty. Uncertainty in the width would be equal to 1 times 10 to the minus 2. Actually, this is plus or minus a centimeter. So this is minus 2, excuse me. 1 times 10 to the minus 2. Let's go ahead and make sure pretty sure I kind of defined that correctly. Ooh, sorry. I did plus or minus a millimeter. Let's go ahead and change those values. It's going to be 1 to the minus 2. So that's going to be a centimeter. Here, just reevaluate. Again, no harm, no foul. So that's actually 20%. Ooh, that's very bad. So we want to make sure, yeah, that's a very, very bad value. But anyways, so you can kind of look at that uncertainty. Excuse me, sorry for that mistake there. People were watching along, but that's why we basically look at these a couple times and solve. But anyways, the only difference would be still have some uncertainty in the width, and then our partials would change. But essentially, that's all you could kind of change in this problem. So the voltages would go away. So we'd have no precision, no voltages we wouldn't have to worry about. So now we just have sigma as a function of m g x over, and then, excuse me, sorry, h. And I'd have, basically, I know I'd have precision error in x. I wouldn't have, and then I'd have basically bias, excuse me, I'd also have precision error, not in x, excuse me, precision error in m. I wouldn't have precision error in my voltage because the voltage is no longer there, but I would have some uncertainty. Basically, I'd have uncertainty in x, uncertainty in h, and uncertainty in w. So I'd have to take those partial derivatives. I'd have bias error there. So that would really be the only thing that changes. So the derivatives would change a little bit, and then you'd have to recalculate it. Great. Draw the generalized measurement diagram for measuring stress using this apparatus. So what's our input? So we want to measure stress. So our first signal transduction, signal processing, and our readout stage. So we do have an additional calibration step. So we calibrate with our basically FCF, our kind of force correlation factor. So what we do here, again, we convert basically a force. So we have a force, and we convert it to voltage using a piezoelectric, and then we convert that voltage back, again, in our kind of readout stage. So this is our sensor transduction stage. So force to voltage. So what's our next stage? Let's kind of read through the problem. Let's see. Is there any kind of filtering or amplification? What's going on here? Let's kind of read back through this problem statement. So we do have a calibration step, but I don't see any filtering. I don't see any amplification, unfortunately, in this apparatus, even though there actually is some. So really, the only kind of factor that we're going to deal with is we're going to have to utilize our kind of equation. So our FCF equation, and then our sigma is equal to FCF times voltage over our width. So that's really all the mathematical operation. So the math operations is going to be going on here. And finally, our readout is just going to be once we plug that back in and calculate that stress. So pretty straightforward again. This is our input. We're going to convert force to the voltage, then we're going to back calculate out to get our stress in our kind of, again, so this is transduction, this is signal processing, mathematical operation again. Is there any filtration? Is there any amplification? Is there any mathematical operation? So signal processing, and then our readout. So that's it. That's your last problem for exam 1. So study well, and again, I think you're going to do great on this exam. So with these problems, always, again, take it a step at a time, break them apart, set up your solutions, and then you'll do just fine. Thanks. I'll see you in the next video.